Kinetic molecular theory. We're going to take a look at the kinetic molecular theory using the website that is available on Blackboard. I think when you download it and look at it, it will look better than it's going to look in my recording. Gases consist of small particles that move rapidly, and mine are not moving too rapidly. Let me see if I can move these up and make them move more rapidly. Now they look like they're moving a little bit more rapidly. They should keep moving at sort of a constant rate. They shouldn't kind of halt and stop here. And when you run this animation, they won't do that for you. Gases will fill the container completely. There are typically large spaces in between them, and sometimes that's really hard to see those large spaces because oftentimes the particles are really way too big. These particles shouldn't even be as big as a pinhead. You always have to make them look too big so that you can actually see them in animations. You should notice that they are moving in straight lines and that they have elastic collisions, and you may note that they change color when they hit. The color has to do with the speed. If you look down at the bottom, you'll see blue, purple, red, yellow, and white. The white ones are moving the fastest, and they have what we call the most kinetic energy. The blue ones are moving the slowest. If I slow this back down again, and if you watch one of the colors when it hits another one, you will see that it often changes color. And this is the idea, and you can see this in ping pong balls. I don't want to say ping pong balls, I mean pool balls. If you hit the cue ball and it hits one of the balls, the cue ball will often stop and the other ball will move on. Well, there's friction in this system. The gas system is a frictionless system, so they don't stop. They keep moving. You will see now I've changed the temperature and I don't have as many of those white ones, which were the fastest ones. Gases are also compressible, and you can see there's lots of room to push things together here. Whereas with liquids and solids, we call them condensed states because the particles are already as close together as they can possibly be. The average kinetic energy is proportional to the temperature in Kelvin, and we have elastic collisions where energy is transferred but energy is not lost. So we're transferring, or we're conserving momentum, and again you can see that by the color change. The white and yellow ones are the fastest ones, and typically when they hit something else they'll slow down and the other particle will get faster. Pressure has to do with how often, how hard they hit the sides of the container. Obviously, if they didn't hit the sides of the container, for example, if this were a balloon, they couldn't keep the balloon's volume, but the balloon's volume is maintained because all these particles are constantly hitting the sides of that container. But how often and how hard, which has to do with how fast they go and how much they weigh. Now, we can change a couple things here, and in fact, if I change the heater temperature, we should see these things. Well, you can see the color change, but you can see that the kinetic energies are spread out, and we have a lot more of the white ones, which represent the fastest ones. Whereas if I drop that temperature down again, you'll see the white ones begin to disappear, and we'll have a lot of what in this blue means cooler, but the slower ones. Also, if I change the molecule count and put a lot more molecules in there at the same temperature, you can see where most of them are blue because I'm at the lower temperature. They are the slower ones. But also, you can imagine that the pressure is going to be greater in this case because there's more particles hitting the surface. Now, if I speed those up, you know, we're really going to have quite a bit of pressure going on, because these particles, there's a lot of them, they're going to hit the surface, the sides of the container often. And by the way, when you're looking at this picture, don't look at it as a flat screen. Consider that you are looking into a bottle, and you are looking really at a three-dimensional group of molecules. So I'll slow it down a little bit and see if we can limit the number of white ones. And you will see that speed plot looks a little bit like a trailing bell curve. We will use this to also look at the gas laws, PV, N, and T, and how they're related to each other. But this way you get a little taste of what this particular program does. You're welcome to use the URL itself and go in and play around with a little of these. Notice I have the heater turned on, and you can change number of molecules, the heater temperature, and there's a few other things that you can fool around with.